today. So I want to briefly summarize what we did in the previous lecture. We saw an example of simple field theory, which arises from vibrations in an elastic medium. So it's a mechanics problem, but of many degrees of freedom. And we saw that we can convert it to a language of quantum particles, and that's the most convenient way of presenting it. Okay, so let me summarize what we did with this example. So this was the example number 1 of quantum field theory that we saw in this course. So vibrations in the chain of masses. So we started from a mechanic problem of many particles that are interacting. Okay, there are a chain of coupled particles, and we converted it to new quantum particles. And these particles are, we call them phonons, because we started from a physics problem of elastic vibrations in a string. But what really it is, it's a set of independent harmonic oscillators, right? And they are characterized by quantum particles, which represent the excitations of this oscillator, and they are represented by the quanta of h bar omega. Okay, so we saw that we could write the Hamiltonian as the sum over k of h bar omega k k plus 1/2. Okay, where AK and AK dagger are the ladder operators of a harmonic oscillator, and they are related to some combinations of the coordinate and momenta of the masses. I'm not, I don't even write the definition because we already did it. But basically, in this language, everything, actually all the physical observables that we could be interested in are represented by this set of creation and annihilation operators, where k are the quantum numbers that represent a wave number. Okay, so they actually correspond to modes of oscillations of this one-dimensional medium. And A is an annihilation operator, A dagger is a creation operator, and this combination, A dagger A, is a number operator. And as a result, first of all, because this Hamiltonian is just a sum of independent terms, also the energy in general, so first of all, okay, before I write the energy, let me mention this is a quantum Hamiltonian, where if we look for a solution of the Schrödinger equation, where now psi is some wave function that describes a many particle system, the basis of eigenstates are states with well-defined occupation of each of the harmonic oscillators. That's all, okay? So, so the set of states can be represented as a series of integer or natural numbers, okay, where each of these numbers for each k is a natural number, and what it represents is the occupation of the oscillator with wave number k. Okay? So if I'm writing a state like this, it means that I have a system where I have many states, many quantum states, and each of them can be occupied by some number of these elementary particles. And these elementary particles are bosons because they can occupy more than one, can be put in the same quantum state. And basically, the set of all possible choices for the n case is a basis for all quantum states. So it's the Hilbert space. The Hilbert space here is spanned by the basis of these states, and they're so these are eigenstates, and their corresponding energy is just a sum over k of h bar omega k n k plus a half. Okay. Good. So, and in this language of particle description, we have a vacuum state where the vacuum is just defined as a state where all the possible k states are empty, okay, so it's just nothing. And above this vacuum, we have our states. Each of them corresponds to some different energy, because the energy is proportional to the frequency omega k of the corresponding mode. And when we think of a state like this, it corresponds to a state where each of the k states, let me write it as okay, h bar omega k1, h bar omega k2, and so on. Each of them can be occupied by 1 particle, 17 particles. Okay, so we can have all these options, and the state is completely, the eigenstates are completely defined by this representation. Okay. Okay, and we also know how does the ladder operator operate on each state, because they are either lowering or rising nk for the corresponding k. So we can compute what any combination of ak and ak daggers, we can compute the states resulting by applying them. It's just like doing the harmonic oscillator, and therefore we can calculate matrix elements, and we can calculate any physical quantity if we can represent it in terms of combinations of these building blocks. Okay? So the problem is completely described in this picture, and it has a very intuitive representation. Now, another thing that I want to stress, what is omega? Omega is just v times k. Actually, to be careful, k is a wave number that may have a sign, but omega is always positive. Okay, so it's actually proportional, linearly proportional to the absolute value of k. with a velocity, and the velocity is related to the parameters of the original elastic string, but in the presentation of the phonons, we actually forgot about the string and the masses and all that. They just come into a parameter. Okay. Now, interestingly, what is this omega k? It corresponds to a dispersion of a freely propagating wave that has a well-defined constant velocity. So actually, it's non-dispersion, right? Omega is just proportional to k. If we plot the dispersion curve in this case, it's actually trivial. It's just a straight line with a slope v, right? Now, here this is represented in the language of waves. So it's a relation between frequency and wave number. But we can, in the particle language, we can convert them to energy and momentum, because what is h bar omega k? If we just multiply by the factor of h bar, we get the energy. Okay, so h bar omega is, let me call it epsilon k. It's the energy of one particle, and h bar k is, we call it pk, is, or p, just p, is a momentum, right? So what is this relation? If we just multiply both sides of the equation by h bar, we get a linear relation between not confused. This is just p. Okay, p as in momentum of a single particle. So we get a relation that energy and momentum are related by a linear dependence. What does it remind us of? It reminds of photons, basically, right? Or basically, more generally, relativistic particles with, however, the velocity of light here is replaced by velocity of sound, if you like, but it has the same form. So this, if I interpret this as some kind of particles that have a particular dynamics, their dynamics is relativistic, because the general relation, if you remember from relativity, sorry, okay, yeah, okay, let me write it like this. Okay, so m naught is the mass, the rest mass of the relativistic particle. I mean, usually you've seen it with c here, the velocity of light. But, okay, so this is what you're familiar with. I hope you're familiar from relativity, right? So here, if m naught is 0, if you have a massless particle, then you get that epsilon is c times p. And here we get something very similar, except instead of velocity of light, we have some other parameter. Okay, so the behavior of these quantum particles is very different and not completely unrelated to the particles we started from. You know, we started with particles like ions in a crystal that have a mass and they're strongly coupled, but they are not good degrees of freedom because they are coupled. The true free particles of the problem are these phonon modes, and they are massless particles, and their dynamics is relativistic, kind of, okay? All right, so all of this we got from a description that is sort of a bottom-up. We started from a microscopic Hamiltonian of masses coupled by strings, okay? And then we went to the continuum limit and derived the field theory, Lagrangian, Hamiltonian, and so on, and that's where we ended. Now there is a second example for a field theory that you have seen in the previous lectures, mainly in the tutorial with SAR, and that's the electromagnetic waves, okay? So once again, this is a simple phenomena that you are already familiar from your second year undergraduate, right? When you studied the wave theory. So there are mechanics waves and there are electromagnetic waves, and the simplest version of each is the case where you have vibrations in an elastic string, or in the case of electromagnetism, this is electromagnetism in a vacuum. Well, now when I say vacuum, I mean the real vacuum of the universe. Okay. And that problem, what you saw in the earlier lectures and the tutorial, is that you can derive a field theoretical description in the form of a Lagrangian and induction from a completely different approach, because here we don't have a bottom-up thing to start. We don't have degrees of freedom that are coupled. We don't even know to formulate it in this language. What we start from is Maxwell equations, right? What we did then is to write Lagrangian by guessing actually a form of a Lagrangian that is the simplest one that obeys all the symmetries, and from it you can derive an equation of motion that should be identical to the Maxwell equation that we all know and love. And that's another way of getting a field theory, and it's top down instead of bottom up. Okay, so you start from something very abstract and constrain it by the clues that you have from the symmetries and from the experiment. Basically, Maxwell equations are derived from observations, right? And that's how you get it. But what I'm going to show you now in the first half of the lecture is that actually if you quantize this field theory that we got in the electromagnetism, you get something extremely similar to this. Okay? In fact, almost the same, up to some minor generalizations. Okay? So these are completely two different physical problems. One is electromagnetism, one is mechanics. Both of them have a wave description, but if you convert it to modes, to Fourier space, you get a particle language, and this particle language for the electromagnetism will be nothing but the good old photons, right? So today we are going to do it systematically. This is electromagnetism. What I'm going to do is to start from the field theory that we wrote in the previous lecture with F mu nu. write it in a particular version of it that is relatively simple to handle, and then eventually quantize it and get this particle description, okay? So that's the logic. Okay, so we can erase that for now. And let me remind you, first of all, what was the field theory that we derived. So it was an action. This is the action, okay? It's an integral over time and the integral over, let's say, a three-dimensional space of a Lagrangian density that is expressed in terms of this antisymmetric tensor F mu. And if we have a matter field like current and charge densities, we also have a current, and J, the current, is a 4 vector, and F is a tensor, okay? And I remind you what is F mu, just the definition. It's the mu A mu minus it's a completely anti-symmetric combination of the derivatives of the vector potential, and the vector A is also a 4 vector. Okay, so A here is, we write it like this, is actually 4 vector where the 0 component, mu equals 0, is the electrostatic potential, and the 3 components, 3 space components, are the vector potential, the space-like vector potential, 3-dimensional vector, okay? This is the definition, maybe, okay, up to a minus sign, but it doesn't matter. Okay, so I hope you have seen and now today I'm going to focus on the case of a vacuum, okay? Where what I mean by vacuum, J mu is 0, okay? No charges, no current, so the Maxwell equations also look very symmetric. And so let me write it explicitly for vacuum, which means J mu equals 0. We get a very simple Lagrangian Z density. Sorry, this is a Lagrangian density, and it has the following form. It's sorry, there is a minus sign. 1 over 16 pi F mu F mu. Okay, this is what it is. The coefficient in units where let's be a little careful with the units. The units are the velocity of flight is taken to be 1. Okay. So then, therefore, the coefficient here is a pure number. Okay. Now, later on, we'll see very easily how to bring back C. Okay, but it doesn't appear in the theory just because it's assumed to be 1. It's a fundamental constant. Okay, now, so this F mu, there are various components with different derivatives in space-time, but we can write various forms of it that are sort of equivalent. in what sense they're equivalent. We know that one of the important symmetries of electromagnetism is a gauge transformation, right? So if I have some representation of the vector potential A, if I transform it by just adding a derivative of some scalar function, okay, this is a gauge transformation. This is a symmetry. It doesn't change the physics, okay? This symmetry is very useful because it suggests that we can choose a gauge, okay? We can choose a gauge and we'll always choose it in the way that the result will be the simplest for our problem. And there are various options, but today let us focus on the case where I choose a gauge that is so-called a Coulomb gauge. So first of all, there is a gauge choice, okay? It's very important. We exploit here a freedom that we have, okay? And we choose Coulomb. What is the Coulomb gauge? It's defined in such a way that the electrostatic potential is 0 and div A of the vector potential is 0. Okay, so the vector potential, the three-dimensional, this is now the three-dimensional space vector potential, its divergence is 0. Okay? Doesn't have to be like that, but that's a gauge choice. Okay? Now, why is it useful? If you plug this constraint in the most general expression for the f mu nu term, you'd see that some terms are cancelling, and I'm not going to do the algebra, but let me just write the result. What is the result? Then you find that L is 1 over, now it's going to be 8 pi times time derivative of A square minus curl A squared. Okay, and this is the Lagrangian density. If you want to find the Lagrangian, you have to integrate over space. Yes?
We can do this specifically in a vacuum because we don't have other restrictions, or
yeah. So if so the vacuum, if you are not in vacuum, there is another term in the Lagrangian. Okay, I remind you, which is okay. Now I think the coefficient is actually just 1. It's this. There's another term, right? In general.
yeah.
Just a scalar product of J and A. And if J is 0, this is 0. Okay?
No, but I asked if the choice of Coulomb gauge, whether we will be able to always do that.
Completely unrelated. So whether J is 0 or not is only the question of whether we have matter particles interacting with
It doesn't like clash with other symmetries?
No. Of course not, otherwise it wouldn't be allowed to write it.
Very comfortable. Surprisingly, like.
Yeah, but it's that's fine. Yeah.
Other system in which, like more complex system in which we'll have additional symmetries which will clash with this kind, or is it?
Okay, actually, you should be a little careful because there could be some state if you do have matter field that interacts with light. There are some states of matter that can appear like they are breaking gauge symmetry, but not really, because gauge symmetry is a fundamental symmetry. Okay? So, I mean, the example I'm thinking of is superconductivity. But if you truly do it carefully, you see that it's gauge symmetry is fundamental symmetry. Okay?
Are there cases in which we will choose another gauge?
You can choose any gauge you like. In fact, maybe I think maybe in one of the homeworks, you'll see, or the tutorial, I think in one of the homeworks.
In homework, yeah.
You have another choice of gauge. Yeah. But this one is very popular for a lot of problems. And, okay. And, let's not, I'm just choosing it to help us to simplify things. Okay? But it's not the only possibility that gives you something simple. It's going to be different, but of course, any physical observable is not dependent on that. Okay? Okay? Okay. But again, there's, by the way, no relation between, so there is, so this term is just not there. We don't consider it, and if there is one, then things are more complicated, and in some cases, you may be able to, we'll see it later on in the course, I hope, you may be able to integrate over the matter field and get some effective electromagnetism, which is going to be more complicated than this. Okay? Not quadratic, for example. Okay? Okay, so we don't want that at this stage. And now I want to start from the simplest equation and just show you, or simplest case, and just show you how to quantize it and get something that looks very similar to what we got for the mechanics problem. So this gauge again gives me this form of a Lagrangian, and I think you can easily recognize the physical significance of this expression, because so if you have no electrostatic potential, just vector potential, what is the time derivative of A? What is how shall we call it? That's electric field. Right? So we have, this is just the electric field, okay? That is given in the special case that there is no electrostatics. So this is just from the Faraday law. And what is this?
Magnetic field.
Magnetic field, okay? So what I actually have here in the Lagrangian is nothing but E squared minus B squared, okay? And if we convert it from a Lagrangian to a Hamiltonian by doing the Lagrange, the Legendre transform, what will we get? You see, it very much looks like kinetic energy minus potential energy. The Hamiltonian that we get will be kinetic energy plus potential energy, so it's just E squared plus B squared, okay? Which you know is Hamiltonian of electromagnetic field in the back. Okay, great. But now what we want, so this is simple enough, but now what I want is to quantize this theory. Okay, so far this is just classical electromagnetism, and I want to quantize it the same way, following the same prescription we define in general. But we have here a problem, an inconvenience, and that is the fact that the second term contains derivative, a space derivative. Okay? So space derivative is not convenient because it's not local. What we do, once again, just like in the case of the vibrations in the string, we go to Fourier space. Okay? So I'm going to take this Lagrangian, actually not this, the full Lagrangian, which is integral over space. Okay, so let me just remind here that the Lagrangian is integral over R of this thing. And I want to rewrite it in terms of the Fourier components of the vector potential. So, so I'm writing here a Fourier decomposition for the vector potential A, which is generally space and time dependent. And this is how it looks like. There is some normalization factor, okay, where this omega is the volume of the system. So suppose you are in a vacuum, but it's confined by some finite volume. Actually, if you want to really discuss the vacuum in an infinite space, you can take this, the limit where omega goes to infinity, but to keep track of the quantization of the modes, usually, this is the usual thing we do. We assume that there are some finite boundaries, some boundary conditions, and we can always go to the limit that omega goes to infinity. So omega is just volume of if you like, a cavity. You can think of a cavity which contains some electromagnetic field. We can take the walls to infinity. Okay? All right, so this is just normalization factor, and now what I have here is a sum over k, and here k is a vector in 3 dimensions. Our problem is 3-dimensional, and I have some fields that I call, basically these are the Fourier components of capital A, which I call alpha k times e to the I k dot r. So notice that I did a Fourier transform only in space. Okay, I converted from R dependence to K dependence. I keep the time dependence. Okay, why do I want to keep it? Because when I write a Lagrangian form, Lagrangian is usually a functional of a field and its time derivatives, right? And from the time derivatives, we can get the momentum fields and all that. So this will be later, but so far this is what we have. And now I want to say something about, so I forgot something very, very important. This equation cannot be right because the left-hand side is a 3-dimensional vector. So these alphas are vectors. And they are vectors in 3-dimensional space. Okay? How many components do they have? 3. In fact, they have 3. No, so this is just the space, okay? Okay, this is this notation is only for the space part of the vector. So fundamentally, there are 3 component objects. So it's a little more complicated than what we know, because for each k, I have different components, but I want to remind you that all of this is correct under an assumption of a particular gauge. And this particular gauge will in fact constrain the alphas so that we need only two components to represent them. Okay? Why is that? Because, so this is just the most general, just a Fourier expansion, right? But when I plug it into the equation that it has a zero divergence, I find that the Fourier components have to satisfy, this is coming from here. Okay? This dictates that if we just plug in the Fourier decomposition in this equation, we find that k dot alpha k equals 0 for each k. Okay? So for each k, what does this mean? That the scalar product of alpha and k has to be 0, namely that alpha has to be orthogonal to the direction of k. Okay? So I give you a k, okay? This is some direction of k. It can be any direction in 3 dimensions. For each k, I can plot a plane that is perpendicular to it, and my constraint actually suggests that, okay, so this is a plane perpendicular to k, and we know that alpha must, I don't know if I'm plotting it very clearly, okay, it's so if I, yeah, it's trying to plot a 3-dimensional plot, but it's the plane perpendicular to k. So alpha has to lie somewhere in this plane. In other words, the vector alpha has to be perpendicular. Okay. Now, therefore, it's confined to a plane. And because of that, it can be generally assumed to be a superposition of only two components, right? So I'm now defining two unit vectors, and they are k dependent. So everything is k dependent. Okay, there's no one axis system that suits all. So I have two direction in this plane. So if let me plot again the plane. So this is the plane that is perpendicular to k. K is going outside of the blackboard, the whiteboard. And here in this plane, I can define two unit vectors. One I call epsilon 1. The other I call epsilon. I put here a hat because they are unit vectors. This is epsilon 2 and epsilon 1. Okay? So there is an index, let me call it lambda, which takes two values, 1 or 2, and this index represents a so-called polarization. Okay, so for each k, I have two polarization modes, and I can write alpha of k as a sum over lambda of epsilon k lambda. Now this is a scalar. Each component is a scalar times epsilon k lambda. Okay? and epsilon are these unit vectors, and I stress that all the direction of the epsilons, or the direction of the plane, is dependent on k. Okay, it's not something constant. Okay, so these are two polarizations. So this is something, I mean, from optics you should know that actually, although the electromagnetic field is in three-dimensional space, these are three-dimensional vectors, actually there are only two, there are only two polarization modes that are independent, and the general alpha vector will be some combination of both, and each of these fields, alphas, are independent mode, okay? And it has two indices, two quantum numbers, if you like. Well, I mean, so far it's not quantum numbers because it's not quantum, but there are two mode definitions. One is k vector, which may be even a continuous variable if we are in infinite space. The other is lambda, that is discrete. It's like spin. Okay, it reminds very much of spin. Okay, very good. Okay, so yeah, and the epsilons are defined in such a way. This is just saying what I plotted here in the drawing, that the vector product of AK1 and AK2 is the unit vector in the direction of this particular K. Okay, that's what we get. Okay, beautiful. So with this expansion in mind, where each of the alpha is a sum over mode, I can now, I then have now a representation of A as a sum over components where the sum is both on K and lambda, okay? And so let me just write it explicitly. It's same normalization factor, the sum over both K and lambda of alpha K lambda of T, epsilon K lambda. This is what determines the vector thing, right? It's a unit vectors, and then I have this exponents that convert it to real space. Okay, so that's the full representation of A, and we plug it into this Lagrangian and get the following result. So I think this part I can only erase and just write what we get, but I do want to keep in mind that C equals 1 until further notice, okay? Okay, so that's what we find for the Lagrangian. Lagrangian is integral over Lagrangian density, and after we do the integration, we get rid of these exponents. This is the usual thing. We get just a delta function. And what we get is very, very simple. There's a factor of 1/2, a sum of K and lambda, where lambda again is running over two discrete values 1 and 2 of, let me write it like this, okay, minus, Well, alpha dot is just time limiting, okay? Because the these alphas are time dependent, okay?
Where did we get the omega from?
Ah, okay. What is omega?
Like, I know it's K, but because
It is K.
Because we know the wave equation.
Yeah. So actually you see how I got it. Yeah. Because if I plug it in here. In Fourier space, it becomes a factor of K, but it's square, right? So therefore, this is just a fancy way of saying
why do you have
omega K is an absolute value of K. Yeah?
Why do you have one term of alpha of K and just multiply by alpha of minus K?
Because it's exactly the same thing that we discovered last week with the case of the phonons. If you have a real field, so A is A of R is defined as a real field. Okay, it's I mean each component is a real function. Okay, therefore it's Fourier components. So when you plug in this kind of term square and you integrate over R, you get a delta function of K plus K prime, and therefore K prime is minus K. Okay. Now, actually, coming back to the quantum version. If you have a real field, a Hermitian field in real space, the Fourier component of it is the Hermitian conjugate of the A of K, alpha of K is alpha of minus K delta. Okay? But I'm jumping ahead because so far I didn't quantize. Okay? But this is just what you get from the mathematics, from the solving the integral and converting to Fourier space. Okay? So yeah, so just like exactly like what we had for the phonons, we had phi k and phi minus k. Okay? It's exactly the same thing. And in this omega, I call it omega because it's actually just k. There should be a velocity here if it was with real units, but this is the velocity. Okay, so in fact, if we bring back the physical units, we should have a factor of c. Okay. So this is a Lagrangian, but we can convert it into a Hamiltonian. This is reminding exactly what we did with the mechanical problem. We first go to a Hamiltonian, and in the Hamiltonian, because we have coordinate and momenta have canonical commutators, we know how to quantize. So we do exactly the same thing, and the first step is to define a momentum, pk. And notice that each of the fields, so it's very similar to what we had with the phonons, but we only have more components because k is a three-dimensional vector, and the lambda, there are two indices, but since they're all independent, it's just a lot more indices, but it's the same kind of thing, right? Each of them is separate in the Lagrangian, and we can define the momentum conjugate to the coordinate. Now let's think of alpha as a generalized coordinate, and we can define a momentum as a derivative of L with respect to alpha dot of the same k and lambda. Okay? This is just a definition. but we see exactly what it is because it just gives you alpha of minus k, right? Okay. So, all right. So, and then we can write. Armed with this, we can do the Legendre transform and get the Hamiltonian. Okay? Let's see how the Hamiltonian looks like.
Shouldn't it be 1/2?
No, because you're doing it twice.
Yeah, exactly. So there is, yeah, there is this half takes care of a double counting. Okay. Yeah, because you see, since k runs on all values, so each k component appears negative and positive. Alpha of some k appears twice. Okay, that's just the usual thing. So this is what it is, and then I'm writing the Hamiltonian resulting from this. It's going to be just very, very reminiscent of the harmonic oscillator thing. A sum over k and lambda of pi k lambda pi minus k lambda plus omega k square, which is just k square, right, times alpha k. So this is just the potential energy. Looks like a potential energy, and this is kinetic energy momentum representation. And once again, the coupling is pi of k couples to pi of minus k. This is a Hamiltonian, and so far it was classical, but now we can easily quantize because we know that alpha and pi obey the quantum operators obey the usual quantization rule. Alpha of k and lambda, pi of k prime and lambda prime. Their commutator is, what is it going to be? I h bar times delta of, so there are actually two deltas. One is of k and k prime, and the other is on the index lambda. Okay? So these are canonical commutators. So we have a quantum Hamiltonian. Okay, if we just replace these pi and alpha by their corresponding operators. But it is not convenient because this form is not convenient because it couples k to minus k. Okay? So what we do, exactly the same thing that we did for the phonons in the mechanics problem. We define new operators, A and A dagger, that are linear combinations of this alpha of k and pi of minus k. And we saw that this works to decouple the modes. Okay? So let me write down the transformation. Actually, if you just look at it and replace the names, we don't even have to, we just have to copy paste from what we did in the mechanics problem. Right, because so I'm not even writing the transformation for the alphas in terms of the A's and A dagger and so on. But actually, let me write it. Okay, so I think this we no longer need it. Erasing it, and so let's write them down. AK lambda is just make sure. So it's 1 over square root 2 of L of K times, and here we have alpha K lambda plus or minus plus I LK square over H bar pi of minus K and lambda. Okay, and a dagger is of course the dagger of this. So this is a alpha of minus K. Why is it alpha of minus K? Because the dagger, I'm once again using the fact that AK dagger is for each lambda. Okay? Just because in real space alpha is a real function in Hermitian, and here I have a minus I LK over H bar times pi of K. Okay, and what is L? L is a length scale. It's units of length, but with units where C equals 1. It's actually defined as H square root of H bar over omega K, where omega, remember, omega is just K, but it's actually C times K. Okay? There is another, so if we want to compare it to the Hamiltonian that we got for the phonons, what are the differences? First of all, let's look at this form. If you look at your notes, or my notes, or from the previous lectures,
there's a coupling.
First of all, there's a little bit of generalization because we have a sum over 2 indices. And the modes are, again, there are 2 polarization modes for each K, and the K is a 3-dimensional vector. But if you compare the results, what we had for the phonons was the kinetic term had a coefficient. What was the coefficient? The factor notice 1/2 I took out of the sum. So what should be the coefficient here? If you start from a mechanics problem, that was the mass of the coupled masses, right? So this is equivalent to phonons with m equals 1, okay, and also C equals 1, which is our unit system, okay? So it's actually a simpler version of that with no parameters, because the only parameter in the electromagnetism in vacuum is the speed of light. There's nothing else, right? So this is a choice of units, and if you bring it back, all you get is that omega now will be C times K and not just K. Okay, that's all. but there's nothing else. So this capital M has no meaning here, okay? Just formally, it's exactly the same expression, okay? And therefore, if you copy-paste, this is how the corresponding scale looks like, and this is the correct definition of A and A, okay? Okay, great. So now we plug in this definition, and we get the final expression for our electromagnetic field. Okay, so the one more thing that I want to stress is, in this we can already erase as well. There's one more thing I want to mention, and that's that the canonical commutators of alpha and pi, okay, which are I, H bar, delta of K, K prime, and delta of lambda, lambda prime. If you plug them into the commutators of A and A dagger, what do you get? First of all, you find that AK lambda with any AK prime and lambda prime, this commutator, what is?
1.
No,
Okay.
both A, it's always 0. Okay, and of course, therefore, its dagger is also 0. Okay, so AA and A dagger are commuting, but AK lambda commutator with AK prime lambda prime dagger is, that's 1, but only if K equals K prime and lambda is lambda prime. So this is actually delta of K prime and delta of lambda prime. Okay, and let's for now assume that the K's are discrete, so we can define separate modes, and everything appears as a sum and not an integral. And then we get, in terms of these new fields that obey this algebra of commutators, I get a Hamiltonian that looks like that. H is just a sum over K and lambda of H bar omega K, A K lambda dagger, A K lambda plus a half. That's all. Okay? Very simple. Once again, it's just a sum of independent harmonic oscillators or harmonic modes, and this A and A dagger can be thought of as creation and annihilation operators of a particle whose energy is H bar omega. Where omega is, now let's bring back the velocity of light to be physical. This omega is just c times k. Here really c is the velocity of light. And therefore, what we get are quantum particles that, just like the phonons of before, they are quantum particles that can occupy a single state to unlimited numbers. So they belong to the bosonic class of particles, and the energy of each particle is actually, to be careful, we can call it epsilon k and lambda, because there's also polarization index, but it doesn't affect the energy. Okay? And this is just h bar of omega. And if we plot energy versus momentum, where momentum is h bar k, once again we get relativistic particles of rest mass 0, which is a photon, as you know. Okay? So this is how we get the photons. Okay? We started from a classical field theory that we derived from symmetry considerations plus constraint of the Maxwell's equation, which are classical equations of motion, if you like. And we found that the quanta or the quantum particles associated with electromagnetism are these massless particles that are called photons. Okay? Okay, great. So to summarize what we did so far is we saw two very, very simple examples of quantization of a field theory, where we started from a many-body problem that contains many degrees of freedom, and we found that in the two cases we were able to write a Hamiltonian that appears like a free gas of some kind of particles. We can characterize everything we want to know about this system in terms of states that are characterized by occupation of these particles in the various modes. Okay? So just again, we have a vacuum. The vacuum state 0 is this, and actually here, if you like, it's kind of the real vacuum. Okay. By the way, the real vacuum is just, you know, the vacuum we know. Okay. It's the vacuum with respect to which what we call particles is defined. We'll see later in the course that sometimes it will be useful to redefine the vacuum. Okay, it's just a reference point. But above this vacuum, I can create electromagnetic fields by adding photons. Okay, and how do I do it? Just like, you know, a generalization of the harmonic oscillator, I apply the creation operators ak lambda as many times as I like, and I get all the eigenstates of this Hamiltonian, and they are of the form nk1, nk2, okay, where n are occupations. Okay, nk, sorry, there's also a lambda. Here I also have, so k is a vector, and in addition to write it more clearly, lambda and k2 lambda 2, okay, and ak lambda is occupation of mode or state k lambda. And by the way, the energy does not depend on lambda. Okay, it's very similar to spin, as we know from electrons. If you don't have magnetic field, the energies are degenerate with the spin. So here it's very similar. And once again, there are two polarization modes for each k. And a general quantum state is defined by how many photons we have in each mode. Okay? These are all the states. And any general state, how will a general state look like? First of all, okay, there's another thing that I wanted to write, which is very general. So I can create such state from the vacuum by applying creation operators. Okay? So how shall I write this? How shall I write this state in this language? This is just the same. This state can be written as a product of k's and lambdas that are represented in this string of occupations of normalization factor nk lambda factorial square root of that times ak lambda dagger to the power nk lambda. All that is acting on the vacuum. Okay, so that's a way to express a state, a quantum state, with some series of occupations by acting on the vacuum with creation operators. Okay? Yeah?
Correct me if I'm wrong, but it seems that the amount of energy that is required to invest in order to perturb a particle is
to create a particle.
Is like it is indifferent to the number of particles that exist already.
First of all, the number of particles is not necessarily so. So in such a state, you have a well-defined number of particles, but it can be anything. Okay, it can be anything. Okay.
So it doesn't matter how many. Like
no, of course. So the eigenstates, so the quantum states that describe the electromagnetic fields, just like any quantum problem, right? You can have various states, and each state has a different energy, right? Here the eigenstates are many-body states, many-body photons, and they can be each eigenstate can be represented as some number of creation operators acting on the vacuum, and they can be anything because these nks, they can be any integer. Okay, and of course as the more photons we have, the eigenstates of this, the eigenvalues of this Hamiltonian will now be here. This will be replaced by nk. Okay, so the more photons you have with higher frequencies, the more energy you have.
But
makes sense, right?
Here it makes sense for the photons, because photons do not interact with each other and they are in some kind of a void. But given that we have like a solid medium, for example.
But we don't, now we're discussing electromagnetism. Before we discussed, let's say, an elastic string, and the modes were not particles, matter particles. They were also photon-like objects, right? They were modes. And these are modes of, just like photons, they were quanta of energy. Okay? The vacuum state in that case was not empty in the like the simplified sense that there's nothing, but it was, we interpreted the ground state of the unperturbed string as a vacuum. Okay? If you like, you can think of our vacuum, the real vacuum. There's no such thing as real vacuum, by the way, but you can think of it as an equilibrium state of some hyper string or hyper elastic medium that is not excited. Okay, and all the particles of any kind are excitations of this vacuum. That's a correct way of thinking about it, about particle physics in general. We know also that you can create particles from the vacuum, right? if you have enough energy, you can create an electron and positron pair. Okay? This happens in the lab, even, right? So, so that you have to get used to. This is the fundamental of field theory, that there's no such thing as, you know, empty void is not really that, but you can have processes that create particles like from nothing, but of course under some rules. You need to have enough energy and you need to have to obey some conservation rules.
So particles that are produced by void are always independent of each other. There is no knowledge of the void.
No, that's a different question, because once there are particles, so if you have a state with particles, now these particles can interact, okay? And actually their interaction can also be interpreted as some kind of, we'll talk about this later, but the forces between particles are, also can be interpreted in terms of this language that they are actually exchanging between them some mediator particles, okay? They're called gauge bosons, but we'll get to it later, okay? I don't want to jump ahead, okay? But what we saw here are two very simple equations that in the end, they gave us exactly the same Hamiltonian. You agree? And it's actually, when you think of the fundamentals, it's not that surprising that we got the same Hamiltonian in this particle language, because in both cases, the theory as we wrote it in real space and time, had kind of a similar form, right? What was special about both the Lagrangian that I wrote and the oscillator, the coupled spring, in both cases, you had kinetic and potential energy that were quadratic, right, in the fields. So it was special, in the case of the elastic medium, it was special to the fact that it's just a harmonic approximation, right? Actually, if we had a potential that is like x squared, it wouldn't give us such a simple form of independent modes. Okay, we'll see that later. But also in the electromagnetic case, we just had E squared plus V squared, right? And it's actually completely analogous to kinetic and potential energy with some generalized coordinates. Okay? So, so the reason that this Hamiltonian has such a simple form, and by simple I mean that all the modes are decoupled from each other, is because we started from quadratic forms, and in both cases it's some kind of a free waves, right, with constant velocity. That is the common factor. Okay? Although these problems are actually very simple, because in both cases maybe we didn't even need all this, because we have a wave equation, we know the solution, we know the physics of it. It's a kind of trivial. But we converted it to a problem of particles, and the next thing that we are going to do in the course is to say it appears like this language of describing a problem is actually very simple. It's a compact way of presenting a problem that here is simple, but if we look at a more complicated problem, maybe we can simplify by using this language. Okay? Now, what is the more general many-body problem we want to solve? We would like to be able to discuss quantum systems of many particles, where the number of particles may not even be well defined, where you can have interactions between the particles, okay, like Coulomb interaction between charged particles. And these are hard problems. These are problems where you cannot make progress with quantum mechanics in the way that you formulated it in your undergraduate, which is in terms of Schrödinger equation and wave functions and all that. So we want to have a new formulation of quantum mechanics that will allow us to address such problems, and that formalism is called second quantization, just for historic reason. But after the break we'll start talking about it, but I want to just start by some motivation why we need it. Why we need it. First of all, yeah, there's something I want to stress about the two examples that I gave you. Yielded a particle description in terms of particles that have a bosonic character, okay? Okay, both the photons and phonons are bosons, but we know that if we look at the particle world that describes our universe, there are also what we usually call matter particles, electrons, protons, okay, atoms, neutrinos. But even if we just think of our, regular materials, atoms, they're made of electrons, protons, and neutrons. And we want to be able to describe problems where there are many such particles, like materials, okay? Properties of materials, including magnetism, conductivity, why some materials are insulators and why some are conducting, etc. All of this is embedded in the electrons in the solid. Okay, if we're talking about solid materials, there are also materials that are like trapped atoms in a trap, or ions. That's another system that we can also be very complicated because you have many particles, many quantum particles. So what is special to all these examples, these latest examples I gave, particularly electrons in solids, which are the main player behind all the phenomena that we characterize materials one from another. What are electrons? They are fermionic quantum particles, right? They obey the Pauli exclusion. So obviously they cannot obey the same algebra rules that we saw with the photons, because they cannot occupy, more than one cannot occupy the same quantum state. All that somehow has to be embedded in a language where we can still introduce something like a creation and annihilation operator for an electron. Okay? Okay, so I think let us now make a half an hour break, and after the break I'll first give you some motivation why we need a new language, and then we'll start introducing it. Okay, and this will be the bread and butter of like the first part of the course. So let's go back to class. So today I'm going to start telling you about a new formulation of quantum mechanics for many-body systems that is called second quantization, and I first want to give you some flavor of why do we need it if we want to consider many-body problems. In other words, why is first quantization not so useful when you have more than one particle, even 2 or 3 are already a big complication. So let me remind you, first of all, the problem we want to solve in any quantum problem is essentially a Schrödinger equation. But now, what is this state or this wave function? It can represent a single particle, as most of the problems that you're familiar with from undergraduate, or it can represent a state with many particles. It can represent a state where the number of particles is not well defined. It's also possible. In the first quantization language, we usually talk about wave functions, right? We write some function of the coordinates of the particles, and we plug it in and hope to get some differential equation that we can solve, okay? Now, so let's assume that we have some quantum problem where we have a set of particles, and for now let us focus on the case that we have only one type of particles, okay? They can be photons or electrons or helium atoms, doesn't matter, okay? Of course, in general you can have more than one kind and they can interact with one another, but one set of particles, and they are defined by some basis of quantum numbers. Let me denote them generally by lambda. And these quantum numbers represent the quantum states, or a basis of quantum states, for the single particle states. So, for example, what can be this lambda? It can be, so it's a quantum number. It can be discrete or a continuous variable, doesn't matter. It can represent momentum or a wave vector. It can represent spin, if we're particles with spins, or polarization. And it can represent, we call it an index I lattice site, okay, if we think of particles that live on some discrete lattice. Some quantum numbers, and there are quantum states, lambda, that are eigenstates of some particular single particle Hamiltonian, okay? For example, if the quantum number k is a good quantum number of a free Hamiltonian, right? If we have just free particles with kinetic energy, k is a good quantum number. And of course, if we have translational invariance, okay, if we have a uniform space, free particles, no potential. So these are these lambdas, and for each such state, we can also write a wave function. Let me call it phi lambda of r. This is a real space representation, which is formally defined as the inner product of the state lambda with the state r. So the state r is just a delta function at some r. Okay? This is something you should be familiar from undergraduate. Okay, so what is the meaning of this wave function? It's a state with a quantum number lambda, which represents a function. It has some values of different r's, and r here is a coordinate of a single particle. Now suppose I have, so one example for such lambda could be the different orbitals in an atom, okay? different orbitals of electrons in an atom. And we know that in atoms that are beyond the hydrogen atom, there are more than one electron, right? So there are different quantum states, and then we can assume that we have some occupation of these states by more than one particles. Like, for example, in the helium atom, there are 2 electrons, right? And so we would like to write, let's talk first about the 2-particle problem, like a helium atom. I don't know if did you look at it in undergraduate quantum mechanics? Helium, like, yeah.
Helium, we did hydrogen atom.
No, hydrogen is single particle.
Yeah, I don't think we ever did.
Okay, because sometimes you teach it anyway, but now let me talk about it, no, not specifically. Suppose we have 2 particles, like 2 electrons in one atom, and there are several available states, discrete states for simplicity. So we can write a wave function that describes the behavior of actually a wave function of 2 particles is something that, just like for single particle, if you take the absolute value square, you get the probability of finding the particles. But here we have 2 coordinates, R1 and R2 for the 2 particles. Okay. Now we can have a wave function that describes, for example, 2 electrons, identical particles, in the same atom. Now, how will and suppose we have a set of wave functions for single particle. Can we just, how should we write this wave function? Can we write this as just a product of 2 wave functions, one of each, with the different coordinates? Will that be allowed?
No.
No, why?
You need an anti-symmetric one.
Exactly, because we know there is another information that once there's more than one identical particle in quantum mechanics, we have to account for its quantum statistics. And we know that in nature there are 2 species of particles, bosons and fermions. Electrons are fermions. They obey Pauli's exclusion. Therefore, the wave function has to be an anti-symmetric combination of whatever wave functions are received. And if there are bosons, it has to be a symmetric combination. Okay, so it's also not just a simple product. So for identical particles, we have the following. Let me write a wave functions of either bosons or fermions, and it has to be up to some normalization factor, and something like phi lambda 1 R1, phi lambda 2 R2, plus or minus. Now the plus or minus depends on whether it's bosons or fermions, of the exchange, namely when you exchange the roles of the 2 identical particles. Okay? Okay, so this is how it looks like if I explicitly write it as a wave function. It's either a symmetrized or anti-symmetrized version. Okay? Okay, so we can also write the same thing as not looking at the space dependence, just as a quantum state that. So what is this? We can represent it as a state lambda 1, lambda 2 that is an overlap with R1, R2. Okay? This is a real space representation of a state that I denote as lambda 1, lambda 2, where what it means, the order here is that particle 1 is at lambda 1 and particle 2 is at lambda 2, but really the form of the state has to be this symmetric or anti-symmetric combination of all the options to permute the particles. So I can write lambda 1, lambda 2 as something like that. Okay, lambda 2 plus or minus lambda 2 lambda 1. Okay, and here the order in the product suggests which particle is which. Okay, and okay, this is for two particles.
Lambda 1 and lambda 2 are basically a different
states, like for example the ground state and the first excited level. Okay. Okay. So so good. And now so you see that now if I want to solve the helium atom, for example, let's assume that basically the spherical symmetry that we had for the hydrogen atom is still holding, is a good approximation, but now we want to find solutions which are of this form. You already see that the problem looks much more complicated than a single particle, because the wave function itself is a superposition of things, and we have two coordinates. And the relative here also the relative and the total coordinate center of mass coordinates, so they are not separable. So it's already two particles is much, even if you have the same potential and the potential is simple, unless it's just a free gas and completely decoupled, it's complicated. Okay. Now. What happens if I go to more than two particles? Let me generalize this expression. Okay, how will the state look like? So if I have, let's say I have a state lambda 1, lambda 2, lambda 3, blah, 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 blah. And here I have n particles. Okay. Okay, so how does it look? What will be the generalization of that? There is some normalization factor that I don't even bother to write, like the generalization of the square root 2, but here, what I have here is it's going to be a sum of many terms. And what are these terms? It's a sum over permutations of the particles. Okay, that's the correct way to write it. And I can write it, if I want to generalize this thing, I will have here, let me now define an index labeled by zeta, which we'll use throughout the whole course. And zeta is plus or minus for bosons or fermions. Okay? That's a definition. Okay? So it's an index that keeps track. If you want to write something compactly, you use this index, and then there's going to be a zeta to the power 1 minus the sign of the permutation. I think it's, yeah, with a factor of half. So that actually you get either 1 or 0. Okay? And the sign of the permutation is whether it's odd or even. Okay? And then it's this factor times lambda of P1 cos lambda of P2, etc. Okay? And product of n things. What does it mean? Okay, what does it mean? So so here I have some order of the particles, 1, 2, 3, 4, 5, until n. Now I do a permutation. 1 turns to 3, 4 turns to 17, okay? And P1 is the permutation of 1, P2 is the permutation, okay? But eventually the number of indices here are the same as here, but they are interchanged, okay? And to go from here to here, I have to do some permutations, and the number of exchanges, if it's odd, it's an odd permutation, and then the sign here will be -1. Therefore, I get a non-trivial factor of -4 fermions. Okay. Whereas if the permutation is even, then for both fermions and bosons it's plus. Okay? So I think you can easily recognize that this is a generalization of this for arbitrary number of particles. Now you see that this is horrible. Okay? So even for 2 particles, this already complicated the simplest Schrödinger equation. Now imagine the wave function itself is it's basically either a Slater determinant or a permanent, which is the symmetric version, and it's just the wave function itself is a sum over large number of if there are large number of particles. If we're interested in the thermodynamic limit that we have 10 to the 23 particles, then we can forget about it, but even for 3, it's unsolvable, okay? As you know, the quantum states of 3-body problem is a very complicated thing. Lev Haykovich here is making his career on this, on some version of this 3-body state, okay? So what I'm trying to convey here, so of course we're not going to use any of this. I just want to mention it because it suggests that just doing first quantization, writing wave functions and plugging into Schrödinger equation is not going to lead us anywhere, okay? It's too complicated, even for the simplest case that the particles are not interacting. If they are interacting, it's even worse because the potential itself depends on more than one coordinate, okay? And it's not necessarily just the relative coordinate. It can be horrible, okay? So, conclusion, we need to drop this to the garbage and replace it by a more useful language. We need a new language, okay? And this language will allow more flexibility and can make progress, and we'll see that it will even give us tools to solve, to some extent, problem with interactions, where we have particles with forces between them, okay? Okay, great. So let me erase all of this and start to develop our second quantization. And the philosophy behind it is that if we have a problem of quantum many-body with identical particles of some type, okay, then we need very little information to characterize a state, okay? just to characterize the state. What characterizes the state? Okay, so first of all, we have quantum numbers lambda, which exactly like I mentioned before. There are some quantum numbers that characterize the single particle states, like the electronic levels in an atom, like K, like spin, etc. Okay, some quantum numbers of single particle. States, and for each lambda we have states lambda, okay, and we also have some energies epsilon lambda, and these are single particle lambdas, okay. So that's a basis of states, and usually we choose the basis according to the specific problem we want to solve. For example, if it is an atom with, or some heavy atom with many, many electrons, for example, what it will be the energy states of the atom, okay, dictated by some potential, and in the simplest case, it may be even spherical. Symmetric doesn't matter, okay? So that's one piece of information we have. Now, for each state, so before I get to this, there's another very important piece of information we need to know about our particles, whether they are bosons or fermions. Okay? Actually, you know, formally you can define something that is in between. But usually you don't find it with elementary particles. This is something that is useful sometimes to introduce in systems of strong interactions as effective quasi-particles. You can have such exotic things. I'm just mentioning it on the side, but we know that the particles that are like the set of elementary particles that build our world are not like that. They have to be, they are constrained to be either bosons or fermions. Okay, so the other piece of information we need is statistics. Bosons versus fermions. We know that they obey different rules, and the different rules are related to the allowed occupations of a single quantum state. Okay, in a sense, okay. So actually, there are two pieces of information that are related to each other. It's the form of the wave function that is symmetric versus anti-symmetric under exchange of two particles. Okay, that's the difference. And it comes together with constraints on the occupation, because we know that fermions cannot occupy the same state because the anti-symmetrization gives you zero, right? Basically, this is okay. So the second piece of information we need to know what is zeta, this zeta, okay? And then once we have some single particle states, so and there is some spectrum, we come with some spectrum of energies, okay? By the way, sometimes you can have such quantum numbers that some energies are degenerate, but still there are different states, so it doesn't matter. In general, every lambda has an epsilon lambda. And now the next piece of information you need to know about your system is how many particles, how many identical particles we have at each state. Okay? Now, because they are identical, that's really the important thing. because they are identical particles, you cannot distinguish between states where you exchange particles on the same state, right? There's no meaning to it. The only meaning is possibly for exchange of particles between different states. Okay, so therefore, you really just need to know the occupation of a given state, and that is what we can call n lambda. Okay, occupation. Now, armed with this information, we see that to characterize a state of any many-body state of such particles, and again restricting to a single species of particles, I can write any state as an expansion in a basis where the basis states are just defined by occupations of each lambda, just like our photons and phonon states. So in fact, the language we used in that case, which emerged naturally from the mathematics of quantizing the field theory, is suggestive as much more general. Right? Any set of identical particles can be represented by a family of states that I will denote as generally as a sequence of occupations. Okay? And this encodes a quantum state where here the ordering is not of particles, it's of quantum numbers, okay? Or like, if you like, positions on this spectrum of states. Okay? So, but on top of this, it's somehow implicit, I need to have the information whether they are bosons or fermions. The examples we saw, we've seen before, were all for bosons. But we would like to be able to do it for fermions as well. Okay? And of course, there should be a difference that will account for this anti-symmetrization thing. Yeah?
If lambda describes the whole quantum state, then how can you occupy more than one fermion?
No, lambda is a quantum state. It's some basis, if you like, a complete basis of quantum states of single particle. Okay, that's what it is.
So it describes the spin and the momentum and everything.
Yeah, depending on the particular problem, yeah.
So
yes.
If two fermions occupy the same lambda,
then if they are fermions, the occupation has to be forced to be only at most one.
Ah, okay.
But that has to come out in the formalism. We have to build it into the formalism somehow. But what I'm saying that the information, you don't need more than that. So you don't really have to keep track of coordinates and what, write them explicitly as exchanging as anti-symmetric of something. No. This is something that compactly represents the state, with buried somewhere should be the information whether there are bosons or fermions, okay, which is a kind of an index that somehow comes in the expressions. Now, but all of these are actually going to be a complete basis of states. But the general state is not generally just one of these. It can be a superposition, right? So in fact, this is a basis, and it's a basis of a space that we call Fock space. Basis it's called Fock space. What is a Fock space? It's a Hilbert space of many-body particles that is spanned by all the possible choices of the n lambdas. Okay? And in fact, there can be infinitely many possibilities, right? And the most general state, many-body state, how I will write it, the most general way, it's a summation over all possible occupations of all the possible lambdas, okay, of there's some coefficients that are, let me write as n lambda 1, n lambda 2, blah, blah, okay, of the state this is the most general state you can write. It's just a superposition. And these are some complex numbers, right? So, for example, you can have, by the way it is defined here, let me just stress what I mean by this notation. All possible occupations, okay? It's so if I order them by some hierarchy that is, by the way, completely arbitrary, but it's sometimes useful to think of it as energy states, okay? It doesn't have to be. It can be lattice sites in the chain or whatever, okay? You define a hierarchy, and within this you have occupations. And this actually means, sum over n lambda 1 going from 0 to infinity, sum over n lambda 2 going from 0 to infinity. That's what this means. I sum over all the possibilities. That any n here can be anything from 0 to infinity. Okay? And I can have states that are linear combinations of a state with 0 particles and a state with, I don't know, one state occupied by 100 particles, and all the rest are empty, or, you know, anything. So this doesn't, actually in general, it doesn't have a well-defined number of particles, right? Because the total number of particles, what is going to be the total number of particles of such a state? These states have well-defined number of particles. What is it? It's just the sum of the occupations, right? So for this state, I can define a total number of particles to be just the sum over all the lambdas in the sum of n lambda. Okay? But if I make a superposition of two or more states with different n, then I get something where there is some uncertainty in the number of particles. Okay? And we'll see later that there are some physical examples where such states are very useful to describe the state, some kind of many-body state. But I can also write a wave function that does have well-defined number of particles, a fixed number of particles n. And how is it going to look? Exactly the same, except that when we sum over occupations, we put a constraint on the sum. Okay? So you can write something like this. I sum over all possible occupations subjected to the constraint that the sum over lambda of n lambda equals n. And then I have my coefficients times n lambda 1, n lambda 2, n lambda 3. Okay?
So that assumes that there is no creation of the structural particles. If we
Yeah. Well, first of all, you describe a state. A state has, okay, a state is either a state, so this kind of state has a well-defined number of particles. It's n, okay? But if you take, for example, let's write, this is with state n, and let us look at psi n. And by the way, the coefficients always have to be normalized, okay, as usual. So let me write down. This is just an example. Okay, I'm allowed to write something like this. What does it mean?
superposition.
It's a superposition of a state with n particles and n plus 1. Okay? In this case, it's an even equal superposition, and therefore, if I calculate, so if I want to look at some physical quantity, for example, the number of particles. The number of particles here is going to be a good quantum number, right? And so the states with well-defined n are eigenstates of the number operator, okay? But if I calculate the number of particles for this kind of state, what does it mean to calculate the number of particles? I have to calculate an expectation value, just like, you know, anything in quantum mechanics. Everything is an operator, and we're allowed to have operators that in some states have uncertainty, and therefore there will be a standard deviation in the number of particles. Okay? It will not be zero for this state. Okay? So, but in any case, what I wrote here is the most general thing. Okay? And so this is called Fock space. It's a state that is defined by the basis states embed this simple information that I mentioned here, and any state can be expressed as a superposition state. Okay? Just like any Hilbert space in quantum mechanics. Okay, now why is this this way? So the way I define the states is very implicit, right? I mean, we still have no idea how to do calculation. It's just calling it by name, okay, and explaining it in words what it means. But we want a mathematical expression that embeds this information and that we can use as a tool to do calculations. And we actually learned from the examples I showed you in the first lectures what is going to be this tool. It's going to be an introduction of ladder operators, of creation and annihilation. Okay? So these are going to be the building blocks of this formulation that we call second quantization. We're introducing a set of creation and annihilation operators. Their physical meaning is that, I mean, they don't really have a physical meaning in the sense that they don't have an expectation value, but their operation as operators, they are defined as something that adds one particle or reduces one particle. Okay? Just like in the harmonic oscillator. Okay? And then if we have such things, we actually know how to write such states in terms of these ladder operators. It's just taking the vacuum. So there is always, in any many-body problem, there is a vacuum. And the vacuum is always the state defined as 0, 0, 0, 0. Okay? So we take the vacuum and apply a dagger of some lambda, and we can apply a dagger of various lambdas various times, depending of if they are bosons or fermions, and then we get our states. Okay? So it's basically something we already seen, but we want to allow these creation and annihilation operators also to describe fermions. And of course, these corresponding operators will have to have a different mathematical structure than the ones we use for the bosons. Okay? All right, so that's the philosophy. And what we want to have is the following, is a set of, once we decided to choose a set of quantum numbers to characterize our single particle states, and we have the statistics, we define a set of creation and annihilation particles for each lambda, okay? For the set of lambdas that we want, that spans our basis of states, and then we need some algebra rules and we also know that what is the state lambda? The state lambda of single particle at state lambda is such that you take the vacuum and apply a lambda dagger once, then you created only a single particle. Okay? Okay. So this is a single particle, but I want to know how to write a general state in our Fock space, where the basis of states are of this form, the set of occupations supplemented by some algebra rules that account for the quantum statistics. So basically I want to know how to define my operators A lambda and A lambda dagger for any lambda. I have to define them according to what they do if they act on such a state. Okay? So, and this is the way to define an operator. Okay? In any basis, you have some basis of states. If you know what A dagger does, or what A does when it acts on some state, arbitrary state, then you can work with it, and then you can ask what happens if I apply A dagger twice or 3 times. What I get if I apply A dagger A, which is the number operator. Okay? Okay. So we start in order to build our. So these are the building blocks. There's a set of states that right now we don't know how to write. But we're going to find that they have the same form as what we wrote before for the harmonic, for the photons and the phonons. What we are missing are these algebra rules. Okay. Okay. So the first stage to build our Fock space is a definition of a dagger. We start by defining the creation operator. If we have a well-defined such operator, we know that we can apply it on the vacuum and generate our whole basis of states. So I'm writing here a formal definition as follows. A lambda dagger acting on let me write here, okay, maybe I'll denote it by I want to give it a number, so okay, let me call it a lambda I. So it's when it acts on a state with general occupations, okay, and now at the ith place we have n lambda I, okay, and the other is some numbers, some series of integers. So what happens if you apply a creation operator over a state that already has n lambda I particles? A dagger creates a state with n lambda I plus 1, right?
Yep.
It increases it by 1 up to some prefactor. Okay, because remember, all the states have to be normalized. So this is what the way we're going to define it. It's n lambda I okay, and I will explain what I mean by that. Actually, I'm out of space, so let me write it more nicely. Write it more nicely. Okay, so it's A lambda I dagger acting on 2 n lambda I at I. It was n lambda I plus 1 with an index zeta that I will soon define what it means. Okay, something that depends on whether they are bosons or fermions. And now I have because I acted only on the occupation of the particles with quantum number lambda I, everything else remains the same, except here at the same ith place I have now n lambda I plus 1. Okay? Now, if I forgot about this zeta, you can easily recognize that what I wrote here is nothing but what you are familiar from the harmonic oscillator, right? This is how the creation operator acts, and this factor of n plus 1 square root is the necessary normalization factor. Okay? However, for fermions, it cannot be just that, right? Because if a fermion, so if let's say the state with lambda I was already occupied by a fermion, if I try to put another fermion, I have to get 0, right? So this doesn't give it, and therefore I have to define this object is defined differently whether zeta is plus or minus. Zeta again is plus for bosons, minus for fermions. So if zeta is plus, then it's nothing but the same number, the same thing, right? So it's just redundant. This is for zeta equals plus. What happens for then zeta equals minus for fermions? I have to define it as n lambda I plus 1 mod 2, modulo 2. Okay, and then that's good because if n lambda I was 0, I get 1. That's good because then I had 0 fermions and some quantum number. I created 1, I get 1. But if n lambda I was 1, I get 2 modulo 2 is 0. Okay, so that's what happens. So if so for fermions, acting with some a lambda on something that has 0 gives me with 1. Okay, but if I this is lambda I, but if I'm acting with the same, I'm trying to create another fermion in a place that is already occupied, it gives me 0. Okay, and that definition serves the purpose. Okay? Very good. Now I forgot one more important thing. Sorry. So in addition to this factor, there is another. Okay, sorry if I try to write it. Sorry about that. Okay. So there is this to the power 1/2, which we already defined, but there is another factor that is just a number, okay? And this number is the same zeta to the power Si, where Si is defined as a sum from, let's say, 1 to I minus 1 of Nj. Okay, so let me explain. So this, in addition to this prefactor, which takes care of the Pauli exclusion, there's another important prefactor, and this is nothing but a number that is either plus or minus. In the case of bosons, it's always plus because zeta is just plus 1. But in the case of fermions, it's minus 1 to the power s, and depending on whether Si is odd or even, you either get plus or minus. Okay? Now what is S? Si. It's called a string. Because it's something that gives us information about all the occupations of all the states up to I. Okay, so imagine that I have my hierarchy of states, and maybe it's the simplest to think of it as the quantum numbers are just positions on a crystal, sites on a crystal. Okay. And I is the ith site, okay? So this string just counts how many fermions I have to the left of this site, Okay? If the hierarchy is corresponding to a spectrum of energy levels, just the same, okay? So I'm looking at a state with energy at, I don't know, some epsilon I, some ith excited level, and this string will count for me how many fermions I have below this, okay? You note that it's kind of arbitrary because the actual number, whether it's odd or even, depends on where we start counting, okay? But this arbitrariness is what we always have in a quantum state. There's always an arbitrary phase, right? We could even multiply everything by some e to the I theta with arbitrary theta, and it's still the same state, right? It's a global phase. So here there's some global minus sign, okay, or global sign that has no physical significance, because any physical significance is only to inner products or to expectation values, okay? Why is it important? Because it keeps track of the occupations of the other particles in such a way that if I now try to create another particle, it matters how many permutations I need to make to get to it, okay? So I claim that this definition of, and actually it is really a definition of the creation operator, is a very precise definition that everything else will follow from this, okay? From here, we can derive some algebra rules about this operator, okay? Okay, and we'll get to what are the algebra rules, but before that, okay, so we have a well-defined definition of creation operator, and it already suggests that we know how to write our most general Fock state, or most general basis state of this type, because how do we get to a state with n lambda 1 in state lambda 1, n lambda 2, etc.? How do we get to it? We start from a vacuum, and we start creating particles, right? And it is easy to see that the result is, so for example, we take our vacuum and we just act with a single, I don't know, a lambda 1 acting on the vacuum. The vacuum is just 0, 0, 0, 0, 0. What is this going to be? This is going to be 1 and then 0, 0. Okay? Now we take, I don't know, a dagger of some lambda 17. What is it going to be? 1, 0, 0, 0, and then 1 in the secondary space. Okay? So you can easily convince yourself by and of course we always have to keep track of these normalization factors when we do that, right? Because if we're talking about bosons, when I apply the same A-dagger more than once, I pick up non-trivial factors of n's, and eventually you can convince yourself that the state, just like what we saw for the case of the photon and phonon examples, we can write the most general basis state as a product over all possible lambdas of normalization factor that is always of this form, right? And then we have a dagger lambda to the power n lambda acting on the vacuum, okay? And this is correct for both bosons and fermions, but for fermions, all the n's here cannot be bigger than 1, okay? For bosons, they can be anything, from 0 to infinity, okay? But still, the formal expression is exactly the same, okay? Okay, great. So we know how to write. Our states, but I keep saying that for fermions, in order for all of this to work, you need the A dagger and A to obey some algebra, some commutation laws that are different from bosons and distinguish them and allow to give this. We don't have always to keep the information, right? It has to come out of the calculation. Okay? All right.
Shouldn't be a factor for the sign of the SI?
So actually, you're right. Okay, so there is actually, you're right. There is some factor here. I'm not writing it. Okay, so let me write it as it's up to, this is true up to a phase factor. I don't want even to write what is the phase factor, but you are right. There is some factor of zeta to some power, but it doesn't come in anything except the only place it comes in is if we take a state and now we apply on it some number of A daggers again, and then it generates new factors. But this is true up to zetas to some power, okay? Which I'm not even writing, okay? And you can always multiply it by an arbitrary phase, and it's still the same state. Okay, so if you like, what it means is that I can use this as my basis. Okay? Instead of writing it like this, I can use this as my basis, and then I don't have to worry about it. Okay, great. So what we are missing here to complete the picture and start doing calculations is to derive some set of algebra rules that tells us what happens if we apply two creation operators or more and keeping track of whether the particles are bosons or fermions. It will not be the same. Okay? All right, so I think we can use this. So okay, so there is something that I'm not going to do in class, but you will do it either in the homework or in the tutorial. I'm not sure which, but it's not a difficult calculation. It's just doing some careful algebra. Suppose I do the following thing. I just take two states. Let me not keep track of lambdas. We just call them I and J. Okay. And I'm now acting on an arbitrary state. state. So now I give different labels to my quantum numbers. Instead of using lambdas, I call them 1, 2, 3. Okay? They're just indices. Okay. So I'm taking any basis state with some occupation, and now I apply a creation operator of J, and after that, a creation operator on I. Now, you notice that these are not necessarily commutative, right? And in fact, if you just take this definition and keep track of this zeta, which distinguishes the meaning of the three-factor here, and also this zeta dependence, you can show directly that what you get is zeta times a j dagger a I dagger, acting on exactly the same state. In other words, if you take any basis state and try to create particle on site I, and then a particle on J, it's not the same as first creating I and then J. Okay, so what is the difference? If you exchange the order of I and J, you pick a factor of zeta. Okay, and it doesn't matter. So this is for the case where I is different from J. Okay, I have to, of course, this is when I is different from J, because if I equals J, what happens if I equals J? So if they are bosons,
it should do the same.
Then indeed they are the same and it's trivial.
Yeah.
Okay? But if they're fermions,
0?
it must be 0. It is 0.
Yeah.
Right? So what I wrote here is correct for I different from J. Okay? But in fact, it is also obeyed for I equal to J. It's obeyed in a trivial sense. Because either both sides are 0, right? So if I plug in I equals J, either both sides of the equation are 0, right? Or they're just equal. You know, it's a tautology. Okay, it's x equal x. Okay. So in both cases, so in fact, I don't even have to put this constraint, but for I different from J, you have to work out the algebra, and you can easily show that this is obeyed. Okay, so this will be in the homework. And now, let me rewrite this equation a little differently. I can deliver this side to the other side of the equation, and I can write it as AI dagger AJ dagger minus zeta AJ dagger AI dagger, all that acting on the same state. And this will give me 0. Okay? I just move this to the left-hand side, and the right-hand side remains 0. Okay? Now, what is the meaning of the expression I wrote here? Here I have some operator that acting on any basis state gives me 0. Therefore, this is a definition of the zero, the null operator, right? An operator that gives me 0 on any basis will annihilate any state, any superposition, right? So it means that the expression I wrote which is some operator, right? It's the זהותית אפס, how do you say it in English? It's the zero operator, okay? The null operator, okay? So this is now an algebraic expression. This is the zeroth operator, and therefore, writing it differently, I can define now a generalized commutator which has an index zeta to be, so I'm writing here a definition, for zeta equals plus, which are a good old bosonic case. We have, this is just A dagger I, A dagger J minus the exchange. So what is it? Just a commutator, right? So this is just what we usually call a commutator.
Just to make sure that I haven't missed anything, you switch from lambda 1 to lambda I to...
Yeah, I changed the name of, I
name.
just changed the name of my quantum numbers to compactify the notation, okay? Yeah. Okay, so for zeta equal plus, it's just a commutator. It's just AI dagger, AJ dagger minus AJ dagger A. Okay? For zeta equal minus, it's going to be something that in the literature we usually denote it with curly brackets, and if explicitly what it is an anti-commutator, namely it's AI dagger AJ dagger plus AJ dagger AI dagger, okay? And this is for, more nicely, this is for plus, and this is for minus. Okay? So this is actually called anti-commutator. Okay? And now, in both cases, we define our creation operators in such a way that this commutator or anti-commutator is zero. Okay? So, therefore, what we get is, let's summarize what we got from it. And again, it just follows from our definition of the creation operator. We get that for bosons, zeta equals plus, we prove that AI dagger commutator with AJ is, which is, if I write it explicitly, it's just this familiar object, commutator is zero, okay? And this is actually true for any ij, right? Because we saw for I different from j, you get it explicitly. For I equals j, it's a trivial statement. Okay? Okay. For fermions, we also get the same, but for the anti-commutator. writing it explicitly. This is an anti-commutator. Equals 0, and actually, again, what does this mean? It means that the operator AI dagger AJ dagger is minus AJ dagger AI. Okay, so you pick a minus sign every time you exchange fermions, and that's exactly what. This is exactly the anti-symmetrization. Okay, so you see, and it all comes from this string. Okay, because we don't care exactly what is the sign here, except if we do a permutation, in comparison, you exchange particles an odd number of times, you get an odd permutation, a minus sign, okay? So this enforces the fermion statistics in a very simple way. You don't have to change a lot, just from commutators to anti-commutators, okay? So that's already a very nice start, but it's only for, yeah?
I wanted to ask if you can explain a bit more why creating particles in different order is exactly the same as switching particles, because I think it's not trivial. It's the same.
It's not trivial, but it's not trivial, I agree, but in practice, if you think of it, you know, an example in real space of particles in different positions, you see that it's equivalent to exchange. But it's just exchanging the roles of the particles, okay? You have some wave function that you imagine, but these are identical particles, that's the thing. So they are identical particles. They are defined by one particle being in some state and the other in other state. Okay. Now what do? You exchange them. You pick a minus. That's what it means. Okay. And this string helps you keep track of it. It's like when you are creating a particle, it also gives a non-trivial phase factor that depends on the occupation of the particles. So fermions are very non-trivial objects. They're attached to them in some kind of gauge field, in a sense. Okay, and it's a very correct way of thinking about it. Okay. So, okay, I think maybe, let me see, okay. I think actually maybe here I will stop, so so keep in mind, so here I'm writing it in terms of the creation operators, but one thing you have to keep in your notes is the definitions. So if you have two operators, now this is a general thing, two operators A and B, a commutator is AB minus BA, an anti-commutator is AB plus BA. And both are non-trivial relations, okay? And this can be defined, this is a definition for any A and B, but in the case that they are creation operators of fermions or bosons, it gives you 0, okay? Okay, so, and the last thing I wanted to say is for the fermions, again, this constraint is true for I different from J, but also when I is equal to J because of the trivial reason that AI dagger square for any I is identically 0. That once again, it's the 0 operator. for fermions. Yeah, for bosons, of course, you can apply it as many times as you want. For fermions, this is the zeroth operator, okay? And for that reason, this anti-commutator being 0 is also trivially correct when I equals 0. It's 0 equals 0, okay? I think here we should stop, and what we'll do next week is, once I defined my creation operator, I no longer have freedom because I know that the annihilation operator is just its omission conjugate, right? So, but I do want to be able to write it in a similar language. Like we know what the annihilation operator will do. It will reduce by 1, but of course there will be some prefactor and we need to keep track of the prefactor. Okay? So this will do, because it requires a bit of algebra, not much. We'll do it next time, but I'm just mentioning that it follows already from this definition. So here we had to make a convention, and from here everything should follow. Okay? And then we'll complete the algebra, and we will get commutators and anti-commutators also for A and A dagger. Okay? And this will complete the algebra we need. Then we'll have all our building blocks to do anything we like. Okay? Okay, so let's stop here.
Thank you.
Have a good weekend.
Yeah.